Very good evening. Good evening to all. This is B. Lakshmi Pravina, Professor BVRIT, Hyderabad College of Engineering for Women. Today we are going to discuss about optimization for training deep models. This is actually the part of our deep learning and neural networks and deep learning. Today we'll cover the contents are how the learning differs from the pure optimization and challenges in neural networks optimization and basic algorithms. First we'll cover with these simple topics and introduction, and in the next video we'll see the remaining part of this optimization of neural networks. So first we'll see how the learning differs from the pure optimization. So here we will see that how the learning models will be differs from the normal optimization methods. The first part of this is the empirical risk minimization. Here we will be thinking of like machine learning is directly usually acts like an indirect method. Whenever we are minimizing our error rate or minimizing the error occurred within our models, okay, there we will use the machine learning as a indirect method. Okay, but generally the goal of this learning is to reduce this particular error or risk minimization. So here we are saying it as a error as a risk. Okay, why? Because the machine learning methods will work in the background, and there we will use the optimization method, that is optimization will be used in the machine learning, and there we will minimize the error rate. Okay, here we are going for reducing of this error rate. For this we will generally use the one is a minimizing of expected loss on the training data set. That is, whenever we are training a particular data set, we will try to minimize that loss of a training of a data set. So here for this we are using a specific cost functions. Okay, these cost functions will play a main role while minimizing of this error rate. So these cost functions can be user defined cost functions, or we can also use the existing cost functions. So next one is whenever we want to minimize this error rate, so then we can also use the indirect optimization is also we can be used to improve the performance of the algorithm or the model. So next one is the surrogate loss functions. Surrogate loss functions is nothing but we are taking a help of other mathematical functions as a loss function, and we can use that loss functions in our machine learning models or deep learning models. So generally whenever we are using these surrogate loss functions, when we will use this is general or normal loss functions are very difficult to be optimized. Okay, so that then in that cases we can use the mathematical functions as the loss functions, and we can use them in our models. So generally the 0-1 loss method is like so h of x comma y, and this will be 1 for the h of x is less than y and 0 for the other values. So in this case, say for example this function is to be optimized, so we cannot use the specific function to optimize. That is, h of x can be any function, so that function is used to optimize this particular loss. So in this case we can also use the surrogate loss functions for the optimization, though that is we can use the differentiable loss functions as the surrogate loss functions, or we can use the robustness of that function can be improved so that we can reduce our error rate. So here whenever we check this graph, there is a blue line which represents the 0-1 loss, and a green line represents the hinge loss, and red line represents the log loss, and another blue line that is light blue line which represents the squared hinge loss, and dotted line as modified Weber loss. So here whenever we are checking these are the different loss functions. So 0-1 loss function is a thick line where it is showing is in the range of a 0 to 1. So here we can use this loss function, which gives the values in the range of 0 to 1. So but remaining all the loss functions are giving a values in the range of a 1 to 5 or 1 to 6 or more than the 6, the like 8 or 9 or more than that. So this 0 1 loss function is giving us very less loss value, so compared to the all other methods. Next one is the mini batch algorithms. This is another type of algorithms which are used for the used to optimize the our model. So here generally for optimizing of our machine learning models, we'll compute the loss functions and or update the parameters, so that we can use either computation of a loss function or we can use the updation of a parameters. So here for this updation of a parameters, generally we can go for the gradient descent method, where in every step we will check for the what will be the our error value or what will be the our loss value. So based on that we can change the our direction or we can change the our parameters. That is, by changing of a parameters we can change the next step to be used or next value to be generated. So this using of this entire training set for every iteration is computationally infeasible. So we can use this for every training set or for every sample of a data we can generate these next values. So these mini batch algorithms are only the samples, examples of each iteration, and here will be used the M as the size of entire training examples, B as the mini batch size. Next one is the batch versus mini batch. The mini batch is nothing but we'll take a small, very negligible samples of data for calculation of the loss and optimization. So batch is it takes a more size compared to the mini batch samples. So mini batch algorithm will improve the optimization, and sometimes it has the poor optimization performance also. So here we'll use after the number of iterations we can the mini batch algorithm is also generally generates the our required optimal value, or it reaches to the optimal state. That is, every time we will take a small samples of a data, and with that we can iteratively repeat the same process and we can achieve to the required sample state. Next we will go for the challenges in the neural network optimization. That is, what are the main difficulties we will face within the while optimizing of a neural networks. So the first one is the limitation of the gradient descent. This gradient descent plays a main role while optimizing of our model. So here the one limitation of the gradient descent is the local minimum value. The local minimum value problem is like, so whenever we are calculating our objective value, the minimization of j of theta, this is our j of theta is our gradient descent method or function. So whatever the function which we are using to calculate the gradient descent, that is the j of theta. So minimizing of this will gives us our next step value, that is the theta t plus 1 is equals to theta t, that is the current state value, minus the summation of differentiation of a j of theta divided by differentiation of a theta value. So that is, you are taking the summation values of your j of theta and theta value differentiations. So here it finds our partial differentiations, gives us the local minimum value. Based on this, say for example, if this value is getting it to be very low, that is very negligible value, then it gets a problem of a local minimum value. Okay. And if this starting point of a gradient descent is chosen as inappropriate, like say for example, if you are selecting a starting value as a random value, or you are selecting a first value of your data set as the initial value, or last value of your data set as a starting value, then it gets a problem. So for this we need to be iterate this process for number of times, and based on that we can take a one value as the appropriate value. Next issue is the saddle point. Saddle point is generally like we can call it as a saturation point. This here for normally for a high dimensional non-convex functions, local minima is act as a rare cases. Local minima is in the fact of a rare cases, where local minima actually has to satisfy the two conditions. The first condition is theta j by dou of that is differentiation of a theta I is equals to infinity for all the I values from 1 to n. Okay. Another one is like dou square, that is double differentiation of j divided by double differentiation of a theta I, which is greater than the infinity value, greater than the 0 or infinity value, which gives us the values for 1 to n. So most of these zero gradient points in deep neural networks are the saddle points. So that is whenever we are getting a value of equals to 0 or greater than the 0, these all points will give us the deep saddle points. So saddle points is here, this red dot is showing us a saddle point, so which is on the line of 0. So that is the static values, that is whatever the points are here are there, those all will be called as a saddle points. That is the around dot, that is around the 0, whatever the values are there, those all are called as a saddle points. The maximum values will get into the saddle points. Next issue is the cliffs and exploding of a gradient. Cliff is a one common issue. One common issue in the objective function for deep neural networks. So where we will get the multiplication of several parameters. That is whenever we are having a maximum number of parameters, and when we are performing a multiplication process, okay, there we can get the issue of a cliff, where we will lead to the issue with the gradient descent. So next issue with the gradient descent is the updating of a step can move the parameter extremely far. That is losing most of optimization works that has been done. That is a maximum optimization task has been performed, and you are trying to make it to the optimized. That is already we got the optimized value, and we are not actually get the better value than that. Then we can go for the issue of exploding of a gradient. So in that cases we are not able to do the any optimization of that. Okay. Next one is the gradient clipping for handling of a cliffs. So this cliff issue we can handle with the help of a gradient clipping. So gradient clipping we can do with the help of this formula by maximizing of it, by maximizing our differentiation of a theta value, we can handle the cliff condition. So here we can reduce the cliff value, that is multiplication value can be reduced. Okay. So in the next video we'll see the basic algorithms. Thank you.